All right. Hi, Year 12s. So for this recording, um, we'll continue with differentiation in terms of applications. With those two exercises, 10C, we're looking at stationary points, and with 10D, we're going to look at different types of stationary points. So let's get started with what it means by a stationary point. I did mention it earlier is when you look at the at a given point on the curve, you will have a tangent. That tangent will have a gradient. That gradient is defined as being the derivative from the limits theorem. So you would have a curve y equals f of x. If for a given point x equals a, the derivative is equal 0, then that point of the coordinates a, f of a for the y coordinate is called a stationary point. So the stationary point occurs when the rate of change of position with respect to time is 0, which is would define as the velocity. That's in a situation when instead of having the x variable, we use a time variable. So at this point, the particle is stationary. So here is the application. You will apply the differentiation rules. So the function is a polynomial. You differentiate, you'll get a quadratic expression. Now, when you want to solve it to make it equal 0, the polynomial needs to be factorized. So here you have a quadratic that you factorize your highest common factor. That's a difference of two squares, and I will give you the two linear factors. Once you have your linear factors, you can apply the null factor law and find the values of x that will make that expression equal 0. You substitute those x values into the function to determine the respective y coordinates, and you end up for a cubic function to get 2 points at which the derivative is equal 0. Let me move my over here so you can see a little bit what you missed out, and let's continue. Another example. Here it's about so as an application, you will differentiate, you will make that derivative equal 0, you will solve for x, but what you're gonna end up with in this situation is they will give you the stationary point coordinates, and with those coordinates, what you do, you need to find, going sort of backwards, you need to find the values of a, b, c. So that should scream to you simultaneous linear equations. So you will need 3 equations. Now what you have as a condition, you need 3 preconditions. So that cubic function has a curve that will go through a point 0, 5, which is a y-intercept. That will give you your first equation. Now the stationary point is actually giving you 2 equations. Now it's giving you a point 2, 7. Those coordinates will give you, using that rule, that will give you a second equation, and the fact that it is stationary is the derivative when x equals 2 will have to be 0. That will give you your third and last equation. So you will do that for 0, 5, for 2, 5. That will give you the first equation is c equals 5. The second equation will be, I know I'm doing it in the same order as I mentioned in outline. So the second point will give you that equation in terms of a, b, and c. C has already been replaced once you get the value of c. Then you use the stationary point definition, you differentiate. That gives you a second equation in terms of AB. That or third equation. So those 2 equations in terms of AB, you solve them simultaneously. Whichever method you use, there's a nice 4 factor in between the two, so you can eliminate a, and you get those values of a and b over here. Okay. You can also use your CAS calculator. So here you have your function that you need to define. So you will define your first function being f of x, and you will need to define a new function being the derivative of f in terms of x. And by solving this, you set up your three equations, f of 0 and so on, with g being the derivative, and you should get the same answers. So let's look at the screens. You define that. Notice here in the question it's given to you as ax squared. I didn't mention it before. Do make sure you either you put not a space but an operator in between. Otherwise, if you type ax, it will assume that it is one variable named with those two letters, and when you're trying to solve it, it will not work out as being separating a and x being a product of that constant and that variable. The derivative, you use those menus, so calculus derivative, you will set the function here. The derivative, you will have to specify the variable x on the denominator. You will call your system of equation. You can use linear. By default it's x, y, z. As you change the number of equations, it will match the number of variables. You can rename them. You write your equations using your functions that are predefined, and you get the solution of that system of equations. And that's the application when you deal with stationary points. Oh, I'm in the way again. Alright, so you get the same answers. Alright, now let's look at stationary points, but they can be different type, and they can be, you will see graphically but also algebraically. Let's look at the graph, which is it can be any kind of function. So usually it would be that could be a cubic. Alright, doesn't really matter at this point, but graphically what you're looking at is your stationary point is when you just use an imaginary ruler, you get your horizontal tangent at those 3 points, A, B, C. And what you do, you scan the appearance of the curve, the trend of the curve before and after. Okay, so A is a local maximum or a turning point. Local mean is it's within a small interval, not across the whole domain. You can see across the whole domain there's no maximum, but between a restricted interval, A will be what we call a local one. The gradient on the left is, if you draw a tangent here, it will go upwards, so the gradient will be positive, and the right hand side will be negative. So if you summarize that in a table, the gradient, which is your derivative, positive before on the left. As your x increases, you get to your turning point, and then on the other side will be negative. So the shape of the curve is ascending, turning point here, and then it's going downwards again. With point B, which is the opposite, it's a local minimum point, you get a pattern also that is summarized here. It needs to be negative first, turning point, and then positive. And that's the shape of it. So downwards on the left and then upwards. With point C, if you notice, the gradient on the left and the right are the same sign, and with the shape of the curve, it's still going to be increasing on either side. That pattern can be also negative on both sides for the gradient, and the curve will be descending on either side. Those points are called stationary point of inflection. Okay, so what we looked at is three different types so far. Maximum as a local, local minimum and two types of stationary point of inflections. Work example, so number 9 from that exercise. So you have a function that is given to you, which is a polynomial. You need to find the coordinates of the stationary point and determine their nature. So differentiate, make it equal 0 because you want to find your stationary points. It gives you two stationary points, one at x equals 0 and x equals -1. Notice that's an x squared, so it means that you will get, just hold on. So to check the nature, you, for x equals 0, you look when you approach 0 from the left and the right, and you look at the sign. So I would test with a value which is below -1, above x equals 1. It doesn't matter which one, you don't really care about the exact value of it, but what matters is the sign. So for x less than 0, when you do -1, that's -1 is actually not going to be a good example in this situation because it's also another stationary point, so you will have to use, let's say, -2. So -2, that gives you a negative, that's a square, doesn't matter, so it will be negative. So it's negative on the left, negative on the right. Hang on, what did I do here? Wait, so it's factorized. Okay, just hold on. Alright, we're back now. Yes, mistake, shouldn't have used -2. What we need to look is for value right below 0 and above 0, but when you below 0, you can't pick a value that is less than -1, so you would have to pick in between, so negative a half, so the derivative is positive slightly on the left, on the right, so you have a stationary point of inflection. With -1 on above, what you have, it's between -1 and 0 from the left, so that's positive. So by doing negative a half, you will look at the sign of this bit, the same as that bit as well, because it's from the right. And below, that's when you can use a -2, that will be negative. A change of sign in a derivative, negative first, positive first, means the curve is descending, turning point, and going upwards again. You have a local minimum point. You can also do a visual inspection from the graph. Okay, so you use a graph page, you type in your expression for your function, so f1 of x. It's graphing, make sure you have your window set properly. You might have to zoom out or manually set your window with your boundaries on the x and the y axis respectively. You can then use the analyze graph, looking for inflection. You specified your interval at which you look for your point of inflection here, and it will give you the coordinates. Okay, you obviously graphically you already have an idea about what kind of point it is. So for example, if I pick this one, I can see it's a minimum, and I would choose the minimum and set the intervals around if I wanted to find the exact coordinates. And that's it for this session. See you later.